Hi everyone. Um, can you guys all hear me? I'm still getting used to the setup. Um, let's see. Um, okay, hi. I guess we can sort of get started now. If everything works. Hi, I'm frodakcin. I am um Shadian invited me to host this stream, so I'll be explaining the problems in this contest. So today was like Codeforces around 9:30. I actually participated. I did okay, I guess, but I'll just be going over the first 5 diff2 problems. So I haven't actually looked at the first 2 yet, so maybe we can do these 2 together. Yeah. Okay. Let me see if there's a better way for me to view chat. Let's do this. Oh, okay. There we go. All right, let's read problem A. Bear with me if this takes a while, because I haven't actually read these problems yet. But once we get to like C, D, E, it'll go faster. I promise. So shuffle party. We're given an array. Okay. Yeah. So we have this swap operation that takes the largest divisor of k, which is not equal to itself. Okay, and then we swap. So we can swap some index with like the index that's the highest divisor of whatever d is, or do k, yeah, of k. Okay, so d is the largest divisor of k, that is not k, and we can swap a, d, and a, k. Okay. Now we perform the swap in this order, and we want to find the first element in the resulting array. Okay. It seems like this problem you can brute force in the sense that you can. Oh wait, no. N is 10 to the 9, so you have to do some math to do this. Okay. Let's take a look. Okay. Okay, so we only care about the thing of position 1, so I guess we have to first think about. So first of all, since the largest divisor of k is definitely less than k, then you would swap everything with something in front of it. And so all we care about is actually I believe, the largest number that is swapped with 1. Let me see if that's correct. Two to n in this order. Give me a second to think about this. I'm actually a little confused by the sample. Okay, wait. Okay. Someone's telling me to solve, like, just to do a example with n equals 10. So let's do that, just so I can get a grasp on what is happening. So I have my iPad set up here. So if I do this, yeah, there we go. then I can turn on my iPad and you can like see me draw. So that's nice. All right, let's do an example for n equals 10 because that'll probably be helpful. Let's see. 1, 2. So after the first swap, we're going to swap 2 and 1. After the second swap, we're going to swap 3 and 1. So it'll look like 3, 1, 2, so on and so forth. Okay, and then 3, 4, 2, 1. And this is all just the first sample. So now 5 will get swapped into the first position. So it should be 5, 4, 2, 1, 3. And then 6 will get swapped to position 3. Yeah, position 3 because 3 is the largest divisor. So 6, 1, 3, 2, and then 7 gets swapped into 1. Is this correct? Oh, it's find the largest number's index. Wait. Oh, it's find the location of 1 after all these operations. I see. Okay. I misread this problem. I thought it was the element that ends up at position 1. Okay. In that case, okay, let's just continue the example because I think it's helpful. So 7 will get swapped with 1. So we will see 7, 4, 6, 3, 2, 5. And then 8 will be swapped with 4. So 7, 4, 6, 8, 3, 2, 5, 1. And then so on. And yeah, as I think people in chat have been saying this, but the thing to notice is that so 1 starts off at position 1, right? And so the number for which the smallest number, so 1 will get swapped with something, and the number that 1 will get swapped with is the smallest number whose largest divisor is 1. And so in that case that number is 2. Because like as you can see 1 will swap with 2, right? And then 1 will be in position 2. And then now we want to see, okay, where's the next position that will be swapped with 1? And so this is where 1 will go next. And so if you remember from our example, what we noticed is that 1 gets swapped to position 4 because the largest divisor, the smallest number whose largest divisor is 2 is 4. And so then 1 goes to 4, and these swap like this. And then if you keep going, like as I did, you realize that the next number that gets swapped with 1 is 8. So at this point, it's reasonable to conclude that the pattern is that it's powers of 2. And so you would want to find the largest power of 2 that's smaller than like these numbers in the input. And at this point, you can probably code it up because that makes sense, especially for a div2a problem. But if you wanted to like understand it a little more and prove it, the reason is that if you consider like a number n and you want to find smallest k such that whatever function this is, such that n is the largest divisor of k. Like in order for n to be a divisor of k must be equal to like some constant times n. And if you want to find the minimum k, you would set this constant to be 2. And so what you get is that the next element that you would swap with is 2n. So now if you think about it, you're just jumping from n to 2n. And if you do that a bunch of times, you're going to get all the powers of 2. Yeah. Well, this part was like, yeah, someone asked me to repeat the power part. like the 1, 2, 4, 8. So the way I did this was I just ran through the example for n equals 10, because someone suggested I do that. And so if we actually do the example, the first array looks like after one swap it looks like this. After 2 swaps it looks like this. After 3 swaps it looks like this, etc. Like if the array is size 8, 1 will end up here. And so if you track the location of the element 1, it starts off at position 1, and then it goes to let me get a laser pointer if I can. See. Yeah, so it starts off at position 1 here. And then it jumps to position 2 and stays at position 2, and then it jumps to position 4. And then it jumps to position 8. So that's where you initially see the pattern of 1, 2, 4, 8. Does that make sense? Nurul? Okay, let's just keep going. I can code this up later if you guys want, but right now the contest is it's in like system testing, so we can't do that. All right, let's look at div2b. This is binary path. So let's read the problem together. So we're given a grid, a 2x(n) grid of 0s and 1s. And yeah, they give us the grid and the input. So now there is a grasshopper in the top left corner that can move right or downwards, and it wants to go to the bottom rightmost cell. And oh, sorry. Yes, thank you, chat. Let me turn okay. There we go. Thank you. Okay, so yeah, I was just reading this over here. Okay, so there's a grasshopper and it moves down to the right. And then our goal is to find the smallest, lexicographically smallest string we can get by going through any available path. And it wants to find the number of paths that does this. Right, so as a quick refresher, lexicographically smaller means that, well, first of all the strings will be the same length because you're going from the top right left to the bottom right, and it'll be exactly n steps where n is the width. And so the definition is if their prefixes are different, then it basically comes first in the dictionary. So the first place that they're different, lexicographically smaller means that the first string's characters is less than the second string's character. Okay, and then it gives a bunch of test cases. That's all fine. Okay, so now let's draw some test cases because that's always helpful. So let me bring my iPad back and we can draw some examples. Okay. Let's look at the inputs aren't that great. So let's just do this quick example. Let's say we have this grid. Actually, let's make it a little bigger. Let's say we have this grid, and it starts with 0, and it looks like this. Now, let me pull up chat again. Sorry. Okay, now it's pretty clear that so the two binary strings that you can obtain are 001 and 011. And if we want to pick the lexicographically least one, we would choose 001, and it appears once. So we want to output 001 and then the number 1. So all paths, so this is sort of the premise of the statement. So let's draw a bigger grid and think about this a little more. So let's look at the second test case. 1 1 1 1 0 0 0 1. So if you notice, all paths are of the form like you go right and then you take a step down and then you go right all the way. So this would be a valid path, and like this would be a valid path, and like this would be a valid path. So let's say that you're choosing some sort of path and you start here and then you have the option of going to the right or going down. One thing you would want to notice is that if you have this sort of choice and the two numbers are different, you would always pick the 0 because it's lexicographically smaller. So we don't want to consider this path at all. And in fact, what's also interesting is that as soon as you decide to go down, at that point onwards, you don't have any more choices. Like, you have to go to the right. So basically, the place that you decide to go down determines the resulting string you're going to get. And I believe that we can try all the strings in a smart way, and we should be able to get the answer. So let's compare like let's compare this path and this path. Actually, okay. So let's actually think about all the paths. We can get the smallest string greedily. Actually, is it true? Yeah, we can. Okay, yeah. So we can. Yeah. So if we do the greedy thing that I was talking about, where you just keep going, moving forward, and if you see a 0, you take the 0. Otherwise, wait. Well, actually, let me think about this. It's not obvious that you can get the smallest string greedily. Yeah. So in a case like this, actually, the smallest string would be going to the right and then down, as opposed to going down and to the right, like this. And so there actually is a little bit of choice involved. But nonetheless, I don't think it's too difficult. So the first thing to notice is that every single string starts at the top left corner, so they all have the same prefix. And this also means that the first character will never be different, and so we don't need to use it to compare. So now let's consider the two paths that we can take. We can either go here or we can go here. So let's say that like so let's just store these two values. So we can go either to this cell here, path A, or we can go to this cell, path B. And then afterwards, let's keep going. So from path A, we can go to the right once more, down, and from path B, we have to go to the right. So in all of these cases, right, the string that we get is 110. So at this point, we haven't made any choices yet, and we can only get one unique string. So from the next position is where it gets a little more interesting. If we go to the right, we see that we see a 0. But if we go down, we see a 1. And if we go from the bottom, we also see the 1. So here we have a choice, and we would always want to pick the 0. So let's write that down. And this also invalidates this place, this square, because we'll never go there. And now, from the last cell, we would only go down. So if we do this sort of greedy thing, we'll always end up with the first part of the answer, which is what is the actual string. Now it's actually a little bit simpler than that, because if we look at if we do this process and we end up at this grid cell, and let's say like this value here is like 0 and the value here is 0, and now you have a choice. You can either go right or go down. in this greedy, you would actually want to always go right. Because if you go right, you have access to both this cell and this cell. Whereas if you go down, right, you only have access to this cell. And so no matter what we do, exactly, yeah. If it's 0 and 1 and they're different, then you would go to the 0. If they're the same, then you would always go right, because it gives you more options. And so if you do this, you can retrieve the string in the end. Okay, so now let's talk about now that we have a string. Someone's saying the camera quality is bad. What does that mean? Is it like the video quality, or? I'll give you some time to answer, because I know there's a little bit of stream delay. So now let's talk about how to compute the answer, which is the number of such paths. Yeah, I'll get to C soon, right after this problem. So here's how I would do it. I know there's like a lot of different ways to. Oh, the reason it's 480p, I'm reading chat. People are saying it's 480p. I think it's because it's a live stream and YouTube takes a little bit of time to make it a higher quality. And I've actually turned it on low latency so I can see the chat faster, and so I think that's causing it to to render faster but at a lower resolution. Yeah. Okay, so the challenge is to count the number of strings. So here's how I would do it. There's a lot of ways, but let me just say the way that I would count it. So remember what I was saying, where the moment you decide to go down, the answer is determined. So what we can do is we can check. Okay, let me construct the binary string first. Let's say it's 1, 1, 0, 1, 0, 0, 1, 0, 0, 1. So the answer would be 1, 1, 0, 0, 0, 0. Okay, so the moment we decide to go down, we know what the answer is. So what I think we can do is we can consider this prefix here is the prefix of the string, and this thing here would be the suffix of the string. So what we need to do is find that, let's give these an index, find that like prefix of 2 matches, and 0, 1, 2, 3, 4, and also suffix of 2 matches. So if this part, right, the 110 matches the 110 of the answer, and the 000 matches the 000 of the answer, then we know that this string is equal to the target string that we're looking for. So now if we're able to check this for every single position, we can count the number of ways that we get the actual answer. Does that make sense, everyone? Okay, I'll just carry on because there is a little bit of chat delay. So, yeah, so someone mentioned, wouldn't that be slow? The answer is yes, that would be slow. However, the thing is, if we think about what the prefix is, the prefix is, like, let's say prefix of I is like a Boolean. And this prefix stores whether or not, like, first I characters of answer matches top row. Now let's say that we know that prefix of, like, let's put a number here, 7 is false. So what can we say about prefix of 8? Well, we can say that prefix of 8 is also false. right? Because if the first sum number, if these don't even match, then there's no way that if we extend them both by 1, it matches. And now let's think, if prefix 7 is true, so let's say like this part and this part, these match exactly. Then what can we say about prefix 8? Well, in fact, to compute prefix 8, we would only have to check if we iterate over n, I'm reading chat again. If we iterate over n and find the prefix and suffix, would that be sufficient? I don't entirely understand what you're saying, but if I understand correctly, you can, yes, that would work if you compute the longest prefix and the longest suffix. And then like you take the difference. That would work as well, yeah. Anyway, so if prefix 7 is true, then prefix 8 is true if and only if these two numbers are the same. And so this thing is equal to, actually let's call it like answer of 8 is equal to, like, let's call this string A and string B. That's B of 8. Or, sorry, A of 8. Does that make sense to everyone? So we can actually compute this prefix away. What do you mean? Someone said you cannot find prefix and suffix in O of n. That's okay. We don't actually need to find the string that corresponds to the prefix. We only need to know if it matches up to a certain point. Right, so this prefix array is just a Boolean, and it means whether or not the prefix matches. We can compute whether or not it matches without getting the strings and doing like string equal equal. We know whether or not prefix 8 matches based on whether or not prefix 7 matches. And so we can actually speed this computation up into O of n. Does that make sense to everyone? And you can do suffix the same way. Okay. Any other approach? There are other approaches. So, okay, we'll call this approach 1. And I think people wanted like people like DP in general. And so there's also like DP ways of thinking about this problem. So let's draw a new grid, and we can do a more of a DP idea. Okay, so compare right and bottom 3 options. 2-pointer. Sure, let me just walk through this idea. So, oh, you want me to code this problem up? Yeah. So it's still pending system tests, but after the system tests, I can code it up. No, so for the DP approach, I'm sure you guys probably know, like, count the number of paths from the top left to the bottom right without going over any, like, if we block some cells, let's do a better example. Yeah. If we block this cell, for example, and you go from the top left to the bottom right, you know how to count the number of valid paths, right? So, the claim here is that, let's say we have this grid here. I was trying to make more cells, but yeah. Let's fill this in arbitrarily. 1 1 0 0 1 0 0 1 1 0 1. So Okay, so my claim is that we're going to start from the left to the right, and we're going to store the number of ways to get to each diagonal. So there's one way to get to the square, and then that means that there's one way to get to the square and one way to get to the square. But here's the thing. If these two numbers are, if the 0 and 1 are different, then we know that we would never actually want to take this one path, because it's strictly less optimal than if you had taken this path. So what we're going to do is we're going to set this value to 0, because we don't actually want to walk that way. So now let's keep going. I'll just put a big exclamation mark here. Yes, if we keep going, we can go from 0 there or down, so we can reach each of these in one way. So now if we keep going, we can reach all of these in one way and two ways, respectively. And then, let's say we get here. There's going to be one way to reach this path, but there's three ways to reach this. But here's the thing. We would never want to take this bottom path here either, because it's worse than if we had taken the 0. So what we can do is we can reset this number to 0. And then we keep going. So this way there's one way to get here, one way to get here, and finally there's two ways to get to 0. Does this method make sense? People are saying in chat that you can't find that approach 1 has problems. I'll code it up later and I'll walk it through you guys. Does this method 2 make sense? Okay, so let's actually now that we have this idea, I'm gonna walk you through okay. People want to move on to C actually. Okay, I'll just go back to these and code it up later. So we'll keep going. We'll keep going to C for now. Yeah. So problem C, I assume people have read it, so I'm not going to read over again. The premise is we have to find the largest XOR of two values. So this is a pretty interesting problem. Thank you to Jagan. He said both approaches are awesome. I hope they're understandable, because that's the goal here, to help you guys understand these solutions. All right, let's talk about C. Let's say the input is n equals 4. Now the first thing to realize is that you can always the maximum XOR you can achieve is all ones. And so like if n equals 4, you have numbers 0, 1, 2, 3, you can always get 7. Or sorry, 3. Because that's all ones. And if n equals 5, which is 0, 1, 2, 3, 4, again you can get 7, which is in binary all ones. So like just a simple proof for this, let's say we have the numbers like 0, 1, 2, 3, 4, 6, 7, 8, 9, 10, for example. Then we can always pick like the largest number, which is 10, and let's say that's OB 10, 10. And our claim is that we can make like 1, 1, 1, 1, right? So the other number that we need to pick is OB 0, 1, 0, 1, which is always going to be less than the original value, and that means that it's always going to be in the set. So we can always get 1, 1, 1, 1. Does that make sense? Yeah, you take the complement, exactly. And because the complement is smaller than the original number, it must always be in the set. Okay, I hope that makes sense. And this idea you can actually straight up implement. So let's get the largest number. How do we do that? Well, it turns out that when you're picking, so the query that you get is like AI or BI, like less than, equal, or greater than. Sorry. What's the array that they use? Oh, PA, PB, less than, equal, or greater, PC, or PD. Yeah, we're on problem C now, for the guy who was asking. What we can do is we can pick A equals B and C equals D. And then what we get is PA less than or equal or greater than PC. And so we can actually compare any two numbers in the permutation. And in theory, if we had any arbitrary number of queries, we can straight up sort the array. And if we sort the array, we can index into it and get any number that we want. But we don't have that luxury. We only have 3n queries. So, the guy in chat, not in the observable universe, he mentions the solution that I use. So that's what I'll be explaining. Yeah. So we can basically sort elements in the array, and instead of sorting it, we can get the maximum value first, and that takes exactly n queries. So max value. So like, let's say like P of A is equal to n. Let's work with an example. Let's say n equals 10. So let's say P of A is equal to 9. So now that we have 9, let's say that's binary OB1001. We want to get this number, 0110. Now this is pretty difficult. In order to extract the location of this number, we would basically have to do nth element on the array, which is like find the nth element in sorted order. So it takes O of n queries, but it's not guaranteed to be in 2 n queries, so that won't work. But our goal is to extract this value. So one observation that you can make is, instead of the XOR operation, if we wanted to do the OR operation, or actually, let's think about it this way. Whatever this number is, we want to find it, but it's very difficult to find. So instead, one thing that we can try to do, since we're given this, in this problem, we're given this OR operation, is to find all numbers such that P like B or P of A is equal to 1111. So now, if we do this thing, then we get like B is in the set B1110. I'm gonna write in binary, so 0110, 0111, 1111. Actually, 1111 is not even in the set. Neither is 1110. See, these are actually the only numbers that we get. Yeah, this is problem C. Yeah, if we consider every number when ORed with this is equal to this number, then we can compute this set. And so the way that we get this set is we say PA or PB, and let's compare this against PA or PC. So if this is less than, then you know that B is not in set. And if this is greater than, we know that C is not in the set. And if they're equal to, then B and C they're either both in the set or both not in the set. And the main thing that we want to realize is that these numbers in this set, let's call it like max or something, when ORed with these numbers gets the largest value. So we want to compute all the numbers that when ORed with A are the maximum. So essentially we want to find argmax of this value. So in other words, all B such that PA or PB is equal to max. Does this step make sense to everyone? That we're able to get all the numbers that such that PA or PB is the largest possible. I assume that it makes sense because that's basically the query that we get. So now we have a bunch of these numbers here. And all of these are complements of 1001. All of these when ORed with 1001, like they result in the target, which is 1111. So now the question is, out of all of these numbers, how can we pick the one such that not the OR operation, but the XOR operation with the original number is the answer? And the observation that you need to make is, let's say that this is the max number. What we want to do is, so all the numbers will be in the form of 1, 1. This can be anything. This can be anything. And like so on. In order for the XOR to be equal to 1, 1, 1, 1, all of the optional values must be 0. And what this means is, since we're enforcing that these bits are 0, it actually makes this number the minimum number in the set. So we want to actually find the minimum in this set here. And in order to find the minimum, we can do the comparison thing that we were doing above to find the maximum number in the list. And that's our answer. Does that make sense to everyone? It's pretty complicated because it's a multi-part. Yeah. You don't have to find n or find 0. Yeah. Does this make sense to everyone? Or is there anything that you would want me to explain? Because I get that this is a pretty complicated problem. Okay, cool, let's move on. Let's see how system tests are going. Still 53, okay. Let's look at problem D now. D is pinball. This problem is fairly difficult. So bear with me for a minute. Now let's run an example. Let's say the example is, have you guys read problem D? Or should I walk through the problem statement or just get to the solution? Oops. Okay, yeah, let's read this problem. Let me put this thing over on the side as well. Okay, let's read problem D. So basically there is a one-dimensional grid. Every cell of the grid has either a less than sign or a greater than sign, and we have to follow the following rules. So if the pinball is on some cell and the character is left, then the pinball will move to the left. Otherwise, if it's on a greater than sign, it will move to the right. The big thing is that after the pinball has moved, the character becomes inverted. So the next time the pinball goes there, it'll go in the opposite direction. And after the pinball leaves the grid, it stops moving. So let's run through the input as an example. Let me bring my iPad back so I can do that. Actually, let's just put these back. There you go. Okay. Yeah, so the example is greater than, less than, less than. And let's drop the ball off right here. So in the first, oh, can you guys see? Oops, let me bring the chat back. Okay, so it's gonna move to the left. And then we're gonna invert this. So this is step 1. Step 2. Step 3 is gonna move to the right. And we're gonna invert this guy. So I'm gonna just draw a symbol on the one that we invert. Okay. And then on the 4th step, we will move the ball here. And we will invert this guy. Let me choose a better color. Yeah. And then on the 5th step, it'll move back to here. Oops. It'll move back to the middle, and we invert the guy on the right. And then finally, we will move the ball to the right while inverting the guy in the middle. And then after the 6th step, the ball falls out of the screen. And so that's why the answer for the test case is 6, if you want to read if you look at the sample. Okay, so I hope that the problem statement is clear. So now let's think about how we actually want to solve it. So let's say the ball is somewhere here, and we have a bunch of right arrows, and then we have a left arrow here. Then the ball is going to jump all the way over to the right here, taking however many steps, but it's going to jump over there. And after jumping over there, the ball will be here, and then all of these arrows will be inverted in this direction. And so in the next step, what we realize is that the ball will actually jump all the way back. So none of these arrows will cause the ball to change direction anymore. So it'll jump all the way back, and it'll jump back to the first right arrow that it sees. Let's say it's that one. And now, actually, I'm going to mark, so it jumps to the first left arrow that it sees. And now what I'm going to do is I'm going to mark every single place where the ball changes direction. So let's circle this guy. And then let's circle this guy. Okay. Now let's keep looking. Now the arrows are all going to be inverted this way until we reach something beyond this point. So now let's say we go here. Now the ball will jump all the way from here to the next left arrow and travel however far that is in that duration. And then it's going to end up here, and all of these guys will be inverted now. So now let's circle this guy. And if we keep going through this process, we're going to jump to the next right arrow. So what we notice is if you look at the original line that we have here, from the location of the ball, every single right arrow to the right of it will cause the ball to change direction to the left. And every single left arrow to the left, every single right arrow to the left of the ball, like these, will cause the ball to change direction. So we actually see why the problem name is called pinball. It's because this pinball is going to bounce between the right arrow and then the left arrow, and then the right arrow, and then the left arrow again. Like right arrow, left, right, left. And keep doing that until it runs out of the screen. Does that make sense? I assume that it does. So now let's keep going. And the problem turns into this. So consider the pinball. It starts off in this position. And let's say it's currently located on a right arrow. So now it's going to keep moving in this direction until it bumps into the first left arrow. And it's going to send everything in the other direction and keep going left until you reach the first right arrow. And then that'll send it all the way back until it reaches the first left arrow again. And then it'll go all the way back until it reaches another right arrow. So let's say that there's no more left arrows to the right of this one. And so afterwards the ball will exit this way. So let's look at this ball's behavior. It starts here, goes here, comes back, comes forth, comes back. Now let's count the number of left arrows here. Let's call this like L. And the number of arrows on the right, let's call this R. So if we're going to have two cases. First case is L is greater than or equal to R. And so in this case, the ball exits on right hand side. And in the other case, if L is strictly less than R, then ball exits on left hand side. Now in the case that there's more things on the left than the right, our answer is going to be, so if the ball exits on the right, then our pattern will look something like this that I've drawn above. And let's give these pinballs like, let's give them indices. So this is located at A, B, this is I, C, D. The total time will be equal to C minus I plus C minus B plus D minus B plus D minus A plus, we'll call this N minus A. So this is a little bit complicated, especially because there's a lot of terms that you need to take care of. But let's think about this in the following way. So I'm going to draw another diagram. So it's going to sit on a right arrow, and it's going to have like left arrows here and more right arrows here. So it's going to travel between this path, oh, I forgot one. I'm just drawing an X underneath the places that the pinball goes. The terms, yes. The terms do not quite cancel. Yes, we use prefix sum for this. That's exactly right. I'm drawing this out because it's a little bit finicky, and you have to do a little bit of edge cases. So these are the paths that we need to count. And if you stare at this for a little bit, you're going to realize that we're going to take, so everything on the right here, like these numbers, we're going to add to the, so if we want to know the distance from here, we want to do like right minus left. And so what we can do is we can add up everything on the right and then subtract off everything on the left. So we want to subtract this, minus, 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 plus, plus, plus. And it turns out that if we use prefix sums, we can get the sum of this plus this plus this in all of one time. and we can get the sum of this plus this in all of one time, and then we can add this and this separately. And so if you do casework in this way, you find that there's a bunch of prefix sums, and if you can compute the prefix sum of this array and then of this array, then we can get that, then we can get the total distance of the pinball travels. And the way I did it, you did casework for like whether or not the ball exits on the right and the left, and so on. Yeah, is this good for everyone? Or is there any part that you would want me to explain? Alright, let's keep going. Speaking of which, let's check the system testing status. How's it not moved at all? I was hoping I'll be able to implement like A and B later, but it seems like the system's stuck. Don't know why. Yeah, I don't know what's going on, guys. It's been at 53% for a while now, and it's still not letting us submit. Let me check the Div 1 contest. Maybe the Div 1 has made some more progress. 32%, wow, that's even lower. I don't know what's going on. Codeforces seems to be having some problem. Anyways, let's go to Div 1E. This is called Pokemon Arena, and oh wait, God, I just realized that my iPad was on this whole time. Oops. Yeah. Okay. Yeah, I was looking at the system testing. I don't know, it's still at 53%, and it's even worse for the Div 1, which is at 32%. And if you look at the status, it seems like not much is really happening. Like if we filter by judging time, it's like, don't know. Yeah. Whatever. Okay, let's just talk about E first, and then maybe we can implement stuff later. So this problem, we are at some sort of Pokemon dueling arena. You have N Pokemon. Initially, the first Pokemon is standing in the arena. Every Pokemon has some attributes. These are basically numbers, just statistics. And each Pokemon has some sort of cost. And our goal is to get the nth Pokemon to stand in the arena. So in order to do that, we have some sort of things that we can do. First of all, we can train the Pokemon. So we can increase a Pokemon stat by some constant, and it'll cause that stat to increase by this constant. Oh, people want my submission for D. Yeah, you can just search it up, but I can just link it as well. Oops. Oh, my submission's here. I admit that my code is not very pretty. Oh, okay, you got it. Oh, I'll just link it anyways. But it should be good enough. Yeah, okay. So we can train a Pokemon and increase its stat by some amount. And that costs K. Or, alternatively, we can choose a new Pokemon. And we can just put that Pokemon in the stadium and have it duel another Pokemon. And if the Pokemon's Jth stat is greater than or equal to the ith Pokemon, then it will win and replace the original Pokemon. Otherwise, the winner will just stay. And yeah, and it costs some amount of money to hire a Pokemon to fight. So now let me write down a few observations for this problem. Yeah, let me please, someone, if any part of this problem statement doesn't make sense, please let me know, because the problem statement is quite difficult to understand. But I'll just write down some observations that'll help us with this problem. The first thing to notice is that we would never hire Pokemon to lose. So we would only hire Pokemon to like replace the arena. Because if we're hiring a Pokemon and it's going to end up losing, then we just wasted a bunch of gold for no reason. The second observation is that you would never want the same Pokemon on the arena twice. I hope this makes sense. The reason is, if a Pokemon, the only reason you want a Pokemon to go on the arena, that's not the nth one, is that you want something else to beat it later. What rating would I give to, for problem E or problem D? I feel like problem D is actually harder than problem E. If you take the time to understand what problem E is actually saying. I have no idea, maybe like 2200. Yeah, I don't know. Problem difficulty is pretty hard to judge, but also its placement probably makes it a little bit harder because people don't do problem E until they've already done problem D typically. Yeah. So the same Pokemon will not enter the arena twice. Then the other thing to realize is that the same attribute will not be used to duel twice. Because if you have, like, let's say your order of Pokemon is like A to B to C to D, and if C beats B on the second attribute and D beats C on the second attribute, then you can save the money of getting C and just straight up having D defeat B on the second attribute. And this holds at I think this holds. It might actually not hold, but the solution doesn't actually care. But it's just a way of understanding the problem better. Question mark. It might not be true. Okay. But let's look at an example of a test case that is sort of interesting for this problem. So let's say that the starting Pokemon has stats of like 1, 100, 100, 100, and the second Pokemon has stats of like 2, 100, 3, 100, and the third Pokemon has stats 100, 100, 4, 5, and then the fourth Pokemon, this is the one that you want to get on the stadium, has like 0, 0, 0, 0. No, that's a bad example. 0, 0, 0, like 7. So if these Pokemon are all free, actually let's add a 0. If these Pokemon are all like pretty cheap, then you would want to get 1, and then have Pokemon 2 beat it on the first attribute, and then go to Pokemon 3, which beats Pokemon 2 on the third attribute, which finally goes to Pokemon 4, which beats it on the fourth attribute. And because some Pokemon have certain weaknesses, the interesting part is like, how do we want to weave our way through the Pokemon to leverage each of their weaknesses and strengths to get our Pokemon on the stadium. And it turns out that this simplifies to a graph problem. So let me walk you guys through the following idea. So each of the Pokemon has some stat. So let's say we have our 4 Pokemon here. 2, 3, 4. And their stats are like 10, 20, 80, 100. The key idea is that if we want to go from Pokemon 1 to Pokemon 2 through this stat, it should be free or it should cost only the price of paying for Pokemon 2 because it has a weaker stat. And same for 2 and 3. So if we can move to the right at a very low cost because in this stat, the Pokemon with greater, like, we don't have to pay for training the Pokemon. On the other hand, if we want to go backwards, if we want to Pokemon 3 to replace Pokemon 4, then we have to incur the cost, which is the difference between their skills. In particular, if we want to go from Pokemon 4 to Pokemon 2, we would need to incur a cost of like 80. If we want to go from 4 to 1, we need to incur a cost of 90. But because because increasing the cost is linear, what we can actually do is we only need to draw the edges for adjacent numbers. Because look, if 100 can go to 80 for 20, 80 can go to 20 for cost 60, then we don't need to draw the edge from 100 to 20 because it's able to take these two edges and go straight to 20. And so if we do something of this nature, we only draw O of n edges. Do you guys sort of see what's happening here? Well, the point is that we only have to draw we only have to draw a small number of edges, and we can capture the idea that Pokemon can beat each other on certain stats. So if we draw this sort of graph for every single stat, right, like say 20, 30, 70, 90, then again we can go up for free because increasing stats is something we get for free, but if we go down, it costs the difference. So now that we have this sort of stat paying structure encoded into our graph, the question now becomes, how can we link these back to the Pokemon themselves? And here's the interesting part. Let's say we have Pokemon 1 here. And Pokemon 1 is really strong in stat 2, but not very strong in stat 1. So let's draw this graph that looks like this. Now, these are going to be bidirectional edges. Yeah, so now, if we go through Pokemon, let's say, so Pokemon 1 is really weak in stat 1, really strong in stat 2. Pokemon 2 is really strong in stat 1, but quite weak in stat 2. Now here's the thing, we can go from Pokemon 1 to Pokemon 2 pretty cheaply by going through this path, right? Because Pokemon 2 beats Pokemon 1 in the first stat, so we can go from Pokemon 1 to Pokemon 2 through this way. And similarly, Pokemon 2 can go back to Pokemon 1 in the second stat, because Pokemon 2 is way weaker than Pokemon 1 on the second stat. And so if we look at this graph, what's basically going on is we take a Pokemon, we choose a stat to battle, and then we can either pay to train the new Pokemon, or leverage the Pokemon's existing strength, and jump to a different Pokemon. And our claim is that if we follow this graph from our starting Pokemon to the ending Pokemon, we actually get the correct answer. Does this make sense to everyone? Yeah, the big idea here is that because the graphs are like one directional and it's linear, we can draw these edges in this way. Okay, yeah, so that's from E. And let me pull up the contest again. Okay. Here's the contest. Let's look at the system test it. Okay. Well, it looks like I'm not going to be able to like get anything done or I'm not able to like code it up and submit it because of the system tests, but let's look at other people's submissions and let's see if we can learn anything from them. Okay, so this guy's solution A. Let's take a look. Let me pull up chat so I can still take a look. Right, so what's this guy doing? Okay, so he's doing, if you guys recall what problem A is, it's this bitwise operation wizard. Oh, this is not the right problem. Shuffle party. Yeah, so this problem, you're given an array and you swap every number with its largest divisor. And so the answer happens to be the largest power of 2 that's less than n. And so this guy takes log of n. I didn't even know this function existed, actually. That's what it does. This is not even the right one. Wow, okay. Let's see what the log function does. Well, this actually doesn't even exist. Okay, let's just look at Stack Overflow. std log. It computes the base 2 logarithm of an integer number and returns the index of the highest bit. Yeah, it must just, yeah. So this guy computes the log 2 of n and then takes it to the power of 2, and that's his answer. Pretty nice solution. Okay, now let's look at a problem B solution. This is binary path. There's definitely a lot of solutions, so I'm very curious to see what types of things we see. Just pull some up. Okay, let's just talk about what they're doing. So, right, it looks like this guy seems to be doing the prefix method that I'm talking about, although I'm not entirely sure. So, alright, so he takes in the 2 strings as input. This is a Kizaru's code. Unfortunately, I don't know who he is, but yeah. So he reads in 2 strings, of course, that makes sense, and he computes the answer. So if he reaches the end, he's going to add the last character. Otherwise, okay, so this is the greedy for the solution. If you guys remember, the greedy is if the 2 numbers are different, so there's a 0 and a 1, you take the 0. Otherwise, you always take the one that moves to the right, because it gives you more leverage and more choices. Yeah, so he's basically saying that if it's better to move to the right, we'll move to the right. Otherwise, we'll move to the left. Otherwise, if we're already on the bottom, we only have one choice, so we take the only choice. That makes sense. And so this is the prefix suffix thing that I was talking about. He computes the longest prefix, so the longest prefix that matches your answer on the top, and then the longest suffix that's matching on the bottom. And the idea is that if the prefix matches and the suffix matches, then you can take the downwards edge and move to the right, and it'll be no problem. In fact, let me get the iPad and let me move this around. Oh, here. This is perfect. Okay, so now you can see what's going on. Right, so if you remember what I was saying with this diagram, that's exactly what this block of code is doing. It's computing, it's basically, so let me draw a better diagram. It's computing the longest prefix that matches, and then it's computing the longest suffix that matches. And then what you know after doing this is that any edge that goes this way is good. So he takes the prefix minus suffix plus 1, and that's the number of places that you can go down. Exactly the number of blocks which are common. Yeah. Look at this guy's submission. This is I don't know if it's actually tourist, but I don't know who this guy is, but this looks like a pretty good solution too. Well, I'm not sure what's going on here. Tourist writes some crazy code. Okay, so he takes the top block and the second block, and then he has this position. Right, so now this is basically saying the two diagonals, so like, if these two guys are the same, right, then we would increase our position. Oh, okay, he has a very, very clever solution. I see. I don't think this is actually Taurus, because Taurus is a div 1 participant, and this is not a div 1 problem. So, I'm not quite sure what's going on there. But, oh man, this is a crazy idea, so I'll explain it though. Basically, what he is saying is that if these two squares are the same number, then now you actually have two paths that you can walk down. You can walk here, or you can walk here. And there's two ways of going there. And the thing is that if you also see that these two cells are the same, then there's one way to reach here, and there's two ways to reach here, because you can go right or down. And if you keep moving in this way, you see that there's three ways to reach here, because again, this top cell always has exactly one way. So the DP table, if you imagine, is like, this is 1 always, because there's exactly one way to get there, and it's keep moving to the right. But here, if there's n ways to get here, there's n plus ways to get here. And so that's what this plus pos is doing. It's saying that if the conditions are correct, then as we move to the right, our DP state looks like 1 and n plus 1. And pos is tracking what that number is. Now, if at some point these two grids are different, so we say like this is a 1, this is a 0, then depending on which one is 0, let's say that this bottom one is 0, which is the not this case, so this case, then you know that we must, let's switch it around. Let's say that the top guy is 0, so S of I is equal to 0, then we must take the top. So now the question is, how many ways are there to go down here now? We can't go through here. This is illegal. So there must be only exactly one way to go here. That's why pos is equal to 1 now. Yeah. And if you're forced to go down, that's also very clever, right? If you're forced to go down here, and like there's one way to get here and n ways to get here, then afterwards, you're never going to go back to the top. So there's only one way to get from here to the end. And so you can just break out and print n. It's quite nice. Does this make sense for you guys? This is a pretty good solution. Alright, let's look at another one. This is some sort of Python solution. Again, they read in the input, they get 2 lists of characters, and then their path is, okay, let's extend the pause equals 1 portion. Oh, did I close it on accident? Here it is. So this part, right? So let me get a new page. Add page. Okay. Now, we're gonna go along. Everything's good until we see a 0, 1. If you think about what the DP table looks like for a moment, it'll look like 1 in this square, 1 in this square, 1 in this square, 1 in this square, 2 in this square, 3 in this square, 1 in this square. Right. I guess actually let's stop here for a second. Oops. Let's stop right here. So let's say the DP state has gone up to this point. So here's where we enter this else block. And we see that this is not true. S of 0, S of I is equal to 0 over here. And so now we reset pause to 1. And I think we can just ignore this. This is just for computing what the answer is. Yeah, I think the divine Aurora is correct. So now, if we have a choice here, we must go to the right. So if we choose to go to the right here, then we have a DP of 1 here, which is good. But our DP over here falls and turns into 0. And so now, because there's only one way to reach this cell over here, the reason he sets it to 1 and not 0 is an off by 1 issue. It doesn't actually matter that much. But the point is that since this guy over here is reset to 0, we have to reset pause to a small number. In this case, it's 1. If you think about what pause exactly computes, it's actually this diagonal here, like the sum of numbers along these diagonals. So pause is initially like pause is 1, and then 2, and then 3, and then on this diagonal, it gets reset to 1. Because of this, if you think about it from the DP's perspective, because this is a 1 and this is 0, you have to take this path, right? You have to take this path. And then so our DP here gets reset to 0. And that's why we set pause back to 1. Is it good with everyone? Yeah. Quite clever, huh? Okay, let's see what this guy's doing. I think, do you guys see enough? Are you guys happy with the B solutions? Or do you want to look at this one as well? Because this Python looks a little bit interesting. Oh, this is exactly the same as Taurus solution, actually. Or not Taurus, but like whoever this guy is, CFGG. It's exactly the same idea. They have a count, the increment. Okay. Yeah. Yeah, so that's the first 5 problems. Are there any questions about these problems as a whole? Like any specifics, any implementations? Like, do you want a walkthrough of like C, D, or E implementation? Or like a re-explanation of anything? Let's give a second for chat. Let me see if I can put this back. Okay, sounds good then. Yeah, that's the stream. Hope you guys. Okay, here's the chat again. Oh, let me delete the iPad screen. All right, that's gonna be all for today. I hope you guys enjoyed the contest. Learned something from the stream. Thanks to Shane for hosting me. Yeah, that's the end of the stream. Thanks for coming, guys.